Here is something a little unsettling about artificial intelligence. It has never once felt embarrassed. It has never cringed at a mistake, never had that stomach drop moment when it realized it got something wrong. It doesn't even know what right means, and yet it learns from being wrong billions of times. That's how every AI you have ever touched got good at its job. The chatbot that finishes your sentence, the app that finds your face in a photo, the system that picks your next video. Every one of them got good the same way, by being wrong over and over and slowly becoming less wrong. So here's the question that runs this whole video. How does a machine that feels nothing, that understands nothing, know when it's wrong? If it can't tell right from wrong, it can never improve. And the answer is almost boringly simple. It's a single number. One number quietly running the entire world of AI. By the end of this, you will know exactly what that number is, how it is built, step by step, with real numbers. The two kinds you will use in almost everything you make. The one mistake with it that ruins more beginner projects than anything else. We are going to take this slowly. Quick hello before we dive in. I am Dr. Subhrajit Nag, and this is Train, where I take the ideas behind AI and actually make them make sense. Usually by hiding them inside true stories you'd never guess were about machines. No scary equations, no jargon I don't explain, just the idea. Let's go. Before we talk about how an AI knows it's wrong, I need to give you a picture of what an AI actually is. Because if that stays fuzzy, nothing after it will land. So forget robots and brains for a second. Picture a machine with a huge number of little adjustable dials on the back of it. Thousands of them. Millions in a big system. Something goes in one end, a photo, a question, the details of a house, and an answer comes out the other. What that answer turns out to be depends entirely on where those dials are set. Change the dials, you change the answer. That machine is what people mean by a model. When a model is brand new, those dials are set at random. So it isn't stupid, it's untuned. Ask it anything and you get confident nonsense. The way a radio tuned to no station gives you static, nothing is broken. It just isn't pointed at anything yet. So the whole job is finding the right dial settings. And that process, this slow, patient turning of dials until the answers start coming out right, is what the word training means. That's all it is. Nobody is teaching the machine anything. Somebody is turning dials. But to turn a dial in the right direction, you first have to know how wrong you currently are. And to know that, you need something to compare against. Which brings us to the last piece. A pile of examples where somebody already knows the answer. Old houses with the price they actually sold for. Photos where a human has already written, "This one's a dog." Because you cannot tell anyone they're wrong if you don't know what right looks like. That pile is called the training data. Right, let's train one. The simplest possible example. An AI whose only job is to guess the price of a house. We feed it one house from our pile, the size, the location, the number of rooms. The dials do whatever they do, and out comes a guess. 7 lakh rupees. And because this house already sold, we know the real answer. 50 lakh rupees. So the model is off by 20 lakh rupees. Now here's the part that trips people up. The model has no idea it's wrong. It doesn't feel that 20 lakh gap. To the machine, 70 and 50 are just two numbers sitting in the dark. Nothing about being wrong registers because there's nothing in there to register it. So for anything to improve, that mistake has to be translated into the only language the machine understands. A number measuring how bad it is. That number is called the loss. You'll also hear it called the cost or the error. Same idea. And the rule is simple. Big loss, you were way off. Small loss, you were close. Zero would be perfect, which with messy real data basically never happens. And now the sentence I want you to carry out of this video. The entire goal of training an AI, every model ever built, from our little house guesser to the giant systems behind ChatGPT, comes down to one embarrassingly simple mission. make that number smaller. That's the whole game. All the maths, all the GPUs, all the jargon. It's elaborate machinery for shrinking one number. And if that sounds too simple, let me show you that you already understand it. Think back to being a kid, playing with hiding game. Somebody hides an object, and as you wander the room, they call out, colder, colder, warmer, you are on fire. You never see the object. You get one word, how close you are, and somehow that's always enough. Look at what your friend was doing. They took the entire position in the room, a complicated, messy thing, and crashed it into a single signal. How far you are from the target. Warmer just meant that number got smaller. That friend was the loss function. And you adjusting each step based on that one word, you were a model training. So we need a number that captures how wrong the model is. Where does it come from? Let's build one by hand with real number. Because once you have watched it happen once, it never confuses you again. Same model, but now 3 houses. House 1, it guesses 52. The real price was 50. House 2, it guesses 60. Real price 55. House 3, it guesses 40. And the real price was 50. Step 1. For each house, find the error. How far off the guess was. 2, 5 and 10. That's our raw material. Nothing clever yet. But we can't stop there. And here's why. We don't want 3 numbers. We want 1. A single score for the model as a whole. So we have to combine them. And the obvious move is to add them up, which is exactly where the first trap is waiting. House 2 was 5 too high. Now imagine another house where it guessed 5 too low. Plus 5 minus 5. Add them and they cancel. You get 0. Your model looks flawless and it was wrong both times. That's why we can't simply add errors up. So step 2, we get rid of the minus signs by squaring each error, multiplying it by itself. 2 becomes 4. 5 becomes 25. 10 becomes 100. A negative times a negative is positive. So every error is now positive and nothing can secretly cancel out. Now you might be thinking, why not just drop the minus sign and be done? That's a completely fair question. You can. That's a real respected loss function and we will meet it in a few minutes. But squaring buys you something extra that dropping the sign doesn't. It changes how big mistakes hurt. Hold that thought. Step 3 is hiding in plain sight. We have 3 squared errors, 4, 25 and 100. We take their average. 4 plus 25 plus 100 is 129. Divided by 3, 43. That's your loss, 43. And why average instead of just adding? Because a real model isn't guessing 3 houses, it's guessing thousands. If you only add, the number keeps growing as you add data. So the same model tested on 1,000 houses would look far worse than on 3. Even though nothing changed, averaging keeps the score fair, no matter how much data you throw at it. Now look at what you just built. You took the error, you squared it. You took the mean, the average, mean squared error. That's the whole scary term. And it's just 3 small steps you just did in your head. Anywhere you see MSE from now on, that's all it has ever meant. Let's sit with that a moment, because there's a fair objection. Why crush everything into one number? Wouldn't the AI learn more from detailed feedback? A full report card of what did well and badly? It sounds reasonable. Here's why one number wins. To improve, a model has to answer one question a staggering number of times. Did that last tiny change make me better or worse? And you can only answer that if you can compare. 43, then 40. That helped. Keep going. 43, then 50. That hurt. Undo it. Instant comparison. No interpretation needed. Now try that with a paragraph of feedback. Which paragraph is better? There's no answer. You would need a human to read and judge every time. Millions of times a second. That isn't feedback a machine can act on. A number is. That's the real reason the crushing down is worth it. The loss isn't there to explain the mistake to a person. It's there to give the machine a direction. How it uses that direction, how it works out, which of its millions of dials to turn, and which way. That's a genuinely beautiful piece of machinery, and it deserves a video of its own. So we are saving it. For today, just hold on to this. The loss is the number every other part of an AI is quietly chasing. So we have built one loss for one kind of problem. But wrong doesn't mean the same thing for every job. And there are two situations you will hit constantly that need two completely different kinds of loss. The first is when your AI predicts a number, house prices, tomorrow's temperature, how many units a shop sells next month. The output is a quantity compared against the real quantity. That kind of task has a name, regression, which is weirdly technical word for something as simple as guess the number. Don't let it intimidate you. If the answer you want is an amount, you are doing regression. And mean squared error is the classic choice. Now let me pay off what I promised. Squaring doesn't just remove minus signs. It changes how big mistakes hurt. And that's the real reason it won. Miss by 2 and after squaring your penalty is 4. Now miss by 10, 5 times further off and your penalty isn't 5 times bigger, it's 25 times bigger, 100. The punishment grows faster than the mistake does. And that's deliberate because it matches how we feel about mistake. Think about an archer, an inch off the bullseye. Nobody cares, good shot. But the arrow that misses the target completely and hits the wall, that isn't just slightly worse. That's the one that matters. The one you fix first. Squaring bakes that instinct into math. So a model carrying one huge error will do almost anything to fix it before polishing the small ones. But sometimes that instinct is wrong, and this is a real decision you will face. Say you're predicting delivery times and your data is sensible except for one bizarre day when a truck broke down and a delivery took 11 hours instead of 1. Square the error and it screams so loudly, the model distorts its own behavior, chasing that single weird day, and gets worse at all the normal ones. That's when you reach for the gentler cousin, mean absolute error. Same idea, but instead of squaring, you take the plain size of each mistake and average those. That strange day still counts. It just doesn't get blown out of all proportion. Rule of thumb, if your biggest errors really are the most important thing to fix, squared error. If freak outliers are just noise, absolute error is steadier. Squared error is the one you'll meet first, and it's a good default. Now, the second big situation, and this one is my favorite because the loss behind it is genuinely clever. Sometimes your AI isn't predicting a number at all. It's making a choice. Cat or dog, spam or not spam. Which of 10 products is in this photo? This is called classification. Sorting things into categories, and it needs a completely different laws called cross-entropy. Scary name, simple idea. Stay with me. First, something about classifiers that surprises people. When a model looks at a photo and decides cat, it doesn't just produce the word cat. Underneath, it produces a set of percentages. It's confidence spread across every option. 90% cat, 80% dog, 2% rabbit, always adding to 100 because it has to pull all its beliefs somewhere. And why build it that way? Because percentages let you measure how wrong it was. Think about it. If all you get is the word cat, then a wrong answer is just wrong. There's nothing to grade, no spectrum, no room for a loss to exist at all. But if you can see it was 90% sure versus 51% sure, suddenly there's something to measure. And that's exactly what cross-entropy does. It looks at those percentages and asks two questions at once. Were you right? And how confident were you when you said it? Here's the analogy that made it click for me. Imagine a test where you don't just answer each question, you also bet on it. Your points scale with a bet. Right answer, big confident bet, huge reward. Right, but you hedged, only half share, small reward. Wrong answer with a big confident bet, you lose a fortune. That's almost exactly what cross-entropy does to a model. So watch it happen. The photo is actually a dog. If the model said a 50% cat, it was wrong, but it was hedging. It didn't pretend to be sure. Moderate slap on the wrist. But if it said, I am 99.9% certain that's a cat and it's a dog, cross entropy comes down like a ton of bricks, not a bit bigger, enormous, because the closer it gets to 100% sure of the wrong answer, the more the penalty explodes, running off toward infinity. Confidently wrong is the most expensive mistake available. And here's why that isn't just clever, it's necessary. In the real world, you don't only use the model's answer, you use its confidence. More than 99% sure? Approve it automatically. Anything less? Send it to a human. That whole idea falls apart if the confidence can't be trusted. A model that says 99% when it means 50 is steering you into mistakes you will never see coming. So, cross-entropy doesn't only teach a model to be right, it teaches it to be honest about how sure it is. It punishes being cocky. And over thousands of examples, the model learns a kind of humility, confident when the evidence is strong, hedging when it genuinely doesn't know. Alright, you now know how to measure wrongness for the two most common jobs on earth. So let me show you the mistake that ruins more beginner projects than anything else, because understanding that is what separates knowing the definition from actually understanding what a loss function is. You are building a model to spot a rare disease in medical scans, and in the real world this disease is rare. Out of every 100 scans, 99 are perfectly healthy and one shows the disease. So you train it and you hand it the most obvious goal in the world. Get the label right as often as you can. Every scan matters the same. Every mistake counts the same. That doesn't just sound reasonable, it sounds correct. Then you check how it's doing and the number comes back 99% accurate. On paper, that's triumph. Except here's what your model actually learned. It's a relentless number shrinking machine with no common sense whatsoever, and it found a loophole. If it simply says healthy every time for every scan without even looking, it'll be right 99 times out of 100. So that's what it does. It stops looking at the scans entirely, and your model is now completely, dangerously useless. But that 1% it gets wrong, that's every sick person. The exact people the whole system existed to find. It misses all of them 100% of the time. Now, look closely at what went wrong, because this is the most important part. The model didn't malfunction. It succeeded perfectly at the goal you handed it. The problem was never the model, it was the number you told it to chase. You said, treat every mistake the same, when what you meant was, whatever you do, don't miss a sick person. Two different instructions, and a model always optimizes the one you wrote down, never the one in your head. The fix is to choose a loss that reflects the real cause. One where missing a sick patient hurts more than a false alarm. So that lazy, everybody's healthy shortcut stops being cheap and starts being agony. But the lesson underneath that fix is what I really want you to walk away with. Because here's the truth about loss functions that most tutorials rush straight past. And AI has no values, no common sense, no idea what actually matters to you or to anyone. It will take whatever number you hand it and make that number smaller, perfectly, tirelessly, without ever once stopping to ask whether it should. It has no wisdom. What it has is your instructions compressed into a formula. Which means choosing a loss function isn't picking maths off a shelf. You're defining for that model what the word wrong means. You're handing it its entire sense of right and wrong in a single equation, and it will chase exactly that, no more or no less, forever. So here's the practical version for when you sit down to build. It's a simple map. Regression, predicting a number, reach for squared error. Classification, sorting into categories, reach for cross-entropy. There are other kinds of tasks with their own specialized losses, but those two cover the vast majority of what you will ever build. And if your model is ever behaving strangely, the loss looks beautiful, but the results are garbage, then before you blame your data, before you buy a bigger GPU, check this first. Is the number I am minimizing actually the thing I care about? 9 times out of 10, that's where the problem is hiding. One last thought. On a small project, the wrong loss gets you a bad house price guesser and a good laugh. When the same mistake logic happens inside a system, learning from millions of people in real time at an enormous scale. It can go somewhere much, much darker. There's a real story about exactly that, but that one deserves a video all of its own. So let's bring it at home. A loss function is nothing more than this, a way of turning how wrong was the AI into one honest number. And all of training every model that has ever existed is just the relentless hunt to make that number smaller. 4 things to work away with. 1. The loss is a single number for wrongness, and smaller is always better. 2. You build it by taking each error, squaring it, and averaging. Literally what mean squared error spells out. 3. For numbers, squared error. For categories, cross-entropy, the one that punishes confident wrong answers hardest of all. And 4. The big one. You choose the loss, so you decide what wrong eventually means. You now understand how an AI measures its mistake, which leads straight to the question I have dodged twice. It has the number, so how does it actually use? How does I was wrong by 43 turn into becoming genuinely smarter? That's a gorgeous piece of machinery, and it's the very next video I want to show you. So subscribe, and if you want the story of how a serial killer ended up teaching us AI, that one's on screen right now.